Pluto is a distant and weird planet that was once a member of our planetary frameworks family. However, recent alarming statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this freezing world is on a possible collision course with Neptune. But how could this happen? Furthermore, what might be the consequences of such a gigantic event? Are we witnessing an interastronomical eccentricity, or is there something more to this looming potential impact? Join us as we examine the possible outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet partly because of its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent projections by leading researchers, Pluto's trajectory is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both sounding the alarm about a potential dangerous impact between these two planets, which could represent a significant risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astounding 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, measured at 17 degrees to the ecliptic plane. The path Pluto follows is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital behavior. One of the most fascinating aspects of Pluto's orbit is its intersection point with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging our expectations of their positions within the planetary system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its peculiar orbit. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out due to its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves predicting how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's akin to predicting their movements based on their initial positions and mutual gravitational pulls. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. The terms azimuthal libration, scope libration, and VZK wobbling are key to understanding this puzzle. According to astrophysicists, what's keeping all planets in their orbits is azimuthal libration. For Pluto and Neptune, this term means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from intersecting. Scope libration, on the other hand, refers to the vertical motion of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is entirely above their orbital plane, providing an additional layer of protection from potential collisions. Another critical factor in this scenario is VZK wobbling, named after three researchers, Vashkovsky, Zelnikov, and Kane, which studied how objects move in space. It involves how three celestial bodies, like Pluto, Neptune, and the Sun, influence one another with their gravity. This gravitational interaction affects their movements. For Pluto, the VZK wobbling helps explain why its path near the Sun is so unusual. Despite appearing chaotic, this wobbling ensures that Pluto moves smoothly over extended periods. These elements work together to keep Pluto's orbit stable, preventing collisions with Neptune or its ejection from the solar system. This three-body problem is crucial for understanding how orbits evolve due to gravitational interactions. Studying this helps us learn more about Pluto, our solar system, and even distant worlds and their stars. Numerical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. Nevertheless, the unique characteristics of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos in check. Recent computer simulations have further clarified how the giant planets, Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit. However, Neptune isn't the sole contributor. Jupiter's gravity also plays a massive role in safeguarding Pluto's orbit, and Saturn helps as well. These simulations show that Jupiter's gravity alone is powerful enough to ensure Pluto remains on a stable orbit for an extended period. Indeed, even billions of years. It's as if Neptune, Jupiter, and Saturn are working together to keep Pluto moving safely in space without encountering trouble. These peculiarities are essential in maintaining order and predictability in space. Without these forces, the solar system as we know it would be far more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their stable orbits, causing a domino effect on other celestial bodies. For Pluto, especially given discussions of a potential collision with Neptune in the future, understanding its orbit is critical. This offers a clearer picture of the dynamic nature of the solar system. Pluto's case illustrates how even seemingly unstable orbits can achieve a state of harmony through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies. Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is vividly demonstrated in Pluto's case. This means that even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using virtual simulations has been immensely helpful for researchers in understanding how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune interact gravitationally. By tweaking small details in the simulations, astronomers can see how even minor changes can make a big difference in Pluto's eventual trajectory. In the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Although features like azimuthal and scope libration help stabilize it, its orbit can still be wild and unpredictable. Even a small difference in where Pluto starts or how fast it's moving can result in a completely different orbit over long timescales. Yet, despite this chaos, Pluto's orbit remains stable for unimaginably long periods, billions of years. This means that Pluto's journey around the Sun has a certain order to it. Even if it appears chaotic at first glance, the long-term stability of Pluto's orbit hinges on gravitational interactions with neighboring celestial bodies, which form a protective balance against catastrophic events. Yet, despite this apparent stability, the inherent chaos within Pluto's orbit leaves room for speculations about potential perturbations over vast timescales. A crucial stabilizing factor is the orbital resonance between Pluto and Neptune. Pluto completes 2 orbits around the Sun for every 3 of Neptune's orbits, ensuring they never occupy the same region of space simultaneously. This synchronized rhythm is maintained through precise gravitational relationships, effectively safeguarding the 2 celestial bodies from collision. Astrophysicists like Tyson and Kaku emphasize the importance of such resonances, likening them to the synchronized movements in a cosmic ballet. Without them, the solar system's delicate equilibrium could be disrupted, potentially leading to orbital chaos or planetary ejections. While current models assure us of Pluto's safety for billions of years, uncertainties persist when projecting far into the future. Factors like interstellar influences, passing stars, or even the gradual transformation of the Sun could introduce subtle shifts in the gravitational dynamics of the solar system. Such shifts might destabilize the resonance between Pluto and Neptune, increasing the likelihood of a close encounter or collision. Moreover, researchers warn of the cumulative effects of minute gravitational perturbations. Over eons, even seemingly negligible deviations can compound, leading to significant orbital changes. This emphasizes the need for advanced simulations and observational campaigns to monitor these dynamics continually. The study of Pluto and its interactions with Neptune serves as a microcosm for understanding celestial mechanics on a grand scale. It highlights the interconnectedness of planetary bodies and the fragility of their seemingly stable configurations. These insights extend beyond our solar system, offering valuable lessons for exploring exoplanetary systems and their dynamics. As technology advances, tools like high-precision telescopes and improved computational models enable scientists to probe these intricate relationships with greater accuracy. Missions to distant bodies, such as the New Horizons spacecraft's historic flyby of Pluto, provide direct data to refine our understanding of such complex interactions. The dance between Pluto and Neptune is a testament to the wonders of gravitational interplay and orbital mechanics. While the prospect of a collision remains a distant and improbable scenario, the very idea underscores the dynamic and ever-evolving nature of the cosmos. As we unravel these mysteries, we gain not only a deeper appreciation of our own solar system, but also a glimpse into the universal forces that shape worlds across the galaxy. Astrophysics is as much about answering age-old questions as it is about embracing new ones. The story of Pluto reminds us that the universe, in all its complexity, is both a source of awe and an invitation to learn. What lies ahead for Pluto and Neptune remains uncertain, but the pursuit of understanding their celestial relationship continues to inspire curiosity and discovery.